therefore I split into half. 30 divided by 2 is 15 points for the midterm and 15 points for the final. From now on, I'll be very strict about the attendance. So make sure that you come and take good notes, and it's very important. All those questions are from the notes, in fact. All right, I'm going to call few names, not all of them, definitely. Ivan, are you there? Ivan Adair, are you there?
Here.
Ivan? Oh, you're there. Very good. Excellent. Ariel Akram. Ariel Akram.
I'm here.
Thank you. Lily Armstrong.
Here.
Grace Badley.
I'm here.
Stephen Arwin.
Here.
Alexander Barrett. Alexander Barrett.
Here.
All right. Jenny.
Here.
Bartlett. Jenny there. Dexton Buncock.
Here.
Kelly Bishop.
Here.
Gillian Bowley. Gillian Bowley. Boyd, sorry. Gillian Boyd. Sorry. Gillian Bowley, yes. Gillian Bowley, not here. Olivia Boyd. Olivia
Here.
Boyd. Jacob.
here.
Yeah, you're fine. Jacob Brehan. Jacob Brehan. Samantha
Here.
Brenner. Samantha Brenner.
I'm here.
Yeah, I got it, Jacob. Jaya Bronson. Jaya Bronson.
Here.
All right. Brina Brownfield.
I'm here.
Danielle Brownlee. Danielle
I'm here.
Holly Brownsberger.
I'm here.
Julia Cadnam. Julia
I'm here.
Cadnam.
I'm here.
Jamie Campion. I got it. Jamie Campion.
Here.
Nathan Caraballo.
Here.
Nabaha Karkido. Nabaha Karkido.
Here.
Grace Grizzly. Grace Sophia Cavatio.
Here.
Jonelle Fuentes.
Here.
Professor,
Yes?
I can see that Grace is here, but like I didn't hear.
Yeah, I'm
so-
here. Grace is here.
All right.
The mic wasn't working.
I got Gina Siachi.
I'm here.
Jennifer Cricket.
I'm here.
Anna Cochran.
Here.
Madeline Coley. Madeline Coley. Melina
I'm here.
Cornell. Melina, who is this? Melina or Madeline? Which one? Melina Cornell. Yes?
Yes. They're
It
both
looks
here.
like, yeah, they're both
Oh.
here.
All right, I got it. Sune Conte.
Here.
Carson Combs.
Here.
Jana Corbin.
Here.
Lindsay Cotlew.
Here.
All right. Taylor Cobb.
I'm here, Professor.
All right, very good. Anna Lynn. Anna Lynn.
I'm
All
here.
right. Oh, you're in there. Please say yes. Okay. Julia Reinhardt.
Here.
All right. Sarah Snyder.
Here.
Anna Stone. Anna Stone. Aileen.
Here, I can see Hannah.
Anna is there. Aileen Stoderman.
Here.
Callum Stringer.
I'm here.
Samantha Tickerhoff. Oh, you're the I just talked to you, Samantha. It's fine. You're fine. Alex Valenti.
Here.
Ron Winsley.
Here.
Jade Whitehead. Jade Whitehead.
I'm here.
Rachel Williams.
Here.
Mason Woodruff.
Here.
Sophia Wells.
Here.
Lindsay Zwicker.
Here.
Jessica Zito.
I'm here.
All right, that's our attendance. Okay, so let's get into that class. Yeah, you're fine. I think let's talk after the class. If you have any question, it's okay. All right, let's get into that day. So test was fine. This test was a little bit off, but it's okay, not that bad. So I'll go through some of the questions that you missed. Many of you missed, frequently missed. So I'll go through those. Okay. Everybody has the test. If not, I'm going to put the test. Okay. Let me put the test again in front of you. And from there, let me go through my application screen and sharing with you. And you tell me what you see. You should see it. Okay. And let me go through this. Okay, so that's the test. Okay, a question that frequently missed, many of you, majority of, not all of you. Okay, question number 2. The oxygenated blood goes inside the machine. After exchanging toxins, the solution present in the machine comes back to the patient via, not be arteries. Comes to the vein, just like if it is similar kind of phenomenon when heart is pumping the oxygenated blood going all over the body, bringing the carbon dioxide and oxygen is delivered. This is deoxygenated blood coming through the veins. Okay. Question number 5.
I have a question. So is the answer to number 2 E or C?
I gave, for some reason, whoever did the B or C, I give the points, okay? But it is a B, you're right. But sorry, it is a C. It is a C because when it's coming to the machine, oxygen is not depleted. Oxygen stays as it is. Yeah, it's a C. But some of you, something happened. But I get the points anyway. All right. So question number 5. Sulfur, after reacting with oxygen, makes sulfur trioxide, SO3, and H2SO4 is the one making it. So it's a B. Okay. Question number 8. Chlorine, after reacting with oxygen, makes Cl2O7. That reacts with the water, makes the HClO4. So the answer is D. Answer is D. Question number 14. Many of you missed, okay? Many of you did okay. Oxygen atom in water has 2 unbonded pair of electrons. One of these pairs is used to coordinate with the protons. So that's a C. It's a C. Question 24. Question 24. The conjugate base and weak acid.
Excuse me, I have a question.
Yeah.
Is there a way for you to send us back all of the questions that we got wrong so we can study for the final?
I will give I'll put the answer today in the blackboard very soon. So this is just discussion. It's okay. I will
Can
do
you
that.
do the same thing for the first exam also?
After exam, I will decide it. I sent it the email. Look at your email.
I didn't get an email.
Everybody got it. Everybody got it. If you did not specifically, just let me know. Okay. Question 24. Welcome. Question 24. Question 24. It's a C. The conjugate base and weak acid for the open system and the closed system. Closed system is HPO4 minus, H2PO4 minus. Many of you missed that one, okay? Many, not too many, of course. Question 29. Question 29. A solution of potassium chloride is the neutral. Potassium hydroxide is a strong, HCl is a strong, neutral. A solution of barium acetate. Barium hydroxide is a strong, acetic acid is weak. So it's a weak, neutral and acid, neutral and basic. Neutral and basic. That is C, 29C. 34. The soft drinks Coke has pOH 8.5. So 14 minus 8.5 is 5.5. It's acidic. So the solution is acidic. Our stomach pH changes 1.02, so that's also acidic. So acidic. 34A. 36. Ethylene, C2H2 has a double bond, so 1 pi bond, and acetylene has 2 pi bonds. So basically it's a B. And 37, it's a Henderson-Hazelberg equation. So definitely it's a acid component is A minus is 0.05 divided by 0.005. It's a 10. Log 10 is 1. Add the 1 to 4.73 is 5.73. It's a B. 38 is the Cl minus is originated from HCl. So say HCl is a strong acid, Cl minus is a weak conjugate base. NH4 came from ammonium hydroxide, it's a weak base. Therefore, ammonium hydroxide is a strong conjugate acid. It's a B, right? 39 is 39 and 40. Everybody answered it just like it took the POH. They calculated the POH and got the answer. But acid, sulfuric acid is not POH, right? So you have to calculate the pH first, and 14 minus that number will give the POH. I told you many times. I give the example many times, but some of you missed it. It happens, right? Same thing is a 40. Barium hydroxide is the base, strong base. So you have to find the POH first, and 14 minus that number will give the pH, right? All right. So these are the things that common missed, and some of you missed probably here and there, but don't worry about it. So I'm going to take the question off. So it will be our, let's see, right. All right, I'm going to close that. And then average was a little low this time, but it's not that bad. It will be better. But once I put the the attendance point, it went very old. Very old. You probably can see your score. And I already submitted to the registrar's office yesterday. I'll do this today for the other sections. So that's basically it's not that bad. All right. Any questions? If you do not have any questions, what I'm going to do is go to the topics. Okay. All right. So now the topics is as follows.
Somebody in the chat asked and said that you consider having a curve. I don't know who said that.
I do not know. Well, carving is not. No, I'm not going to do the carving at this time because many of you, in fact, got 100% and above. 100% and above. So that's basically, if I carve it, it will be 150 or 125 or 30% above for those. So definitely not carving at this time. I'll see, because many of you did exceedingly well. So that's the main most important part. All right. So not carving at this time. Okay. Now let's go to the topics. Let's go to the topics. What we are going to discuss. All right. So let me open this thing, and you tell me whether you can see it or not. If not, then we'll talk about. I'll see what's going on here. So this is the last slide that we talked about. Let me open it for you, and it's opening. For some reason, I closed it. Oh, I think my computer is updating things at this time of the day. All right, fine. All right. So give me a second here, okay? I'm opening the slide, and let's see where am I. Okay. This is updating for some reason at this time of the day. I don't understand why, but that's okay. Did it. All right. So let's go through. Tell me, this is the last slide or not? Is it okay? Is it the last slide talked about? Yes?
Yeah.
Yes. Now, what will be in the third test? Please write down. I'll tell you again, but was before the exam. But I know I may not tell many times. So please write down what will be for the third test. The third test will include details of Lewis dot structure. The Lewis dot structure. Remember, I did not ask many questions, and I told you everybody that this time I'll have only a few questions, only the basic principle of making molecular compounds, and that's basically did by sharing a pair of electrons with the octet rule, etc., etc. And you answer the question too. And then I also told you that pi bonds and sigma bonds, the differences between those two, and you already did that. That's the only two questions I asked. For the third test, I'll have a details of how to draw Lewis dot structure, LDS, Lewis dot structure. You must remember the total number of electrons, how to distribute the electrons. Questions will be entered in many different ways. And they always do that just to fulfill the octet rule. Octet rule. In some cases, as you probably saw, some cases, there is some exception to the octet rule. An exception to the octet rule is because of the elements in the third period, period 3, that includes but not limited to sulfur, phosphorus, chlorine, etc., etc. They can have 3ps2, 3p6, say 8 electrons. In addition to those two orbitals or subcells, they can also have 3d10. In other words, they can use the 3d empty subcell to coordinate or to make a covalent bond with some other elements. That's exception to the octet rule. You must remember those, study those. Next, study the three-dimensional structures of the molecular compounds. We talked about the Vesper model. We also talked about the different types of structures, 3D structures, like AX4 is a tetrahedron, right? And 109.5 degrees for the perfect bond angle. And why it is so? Because those electron clouds, each bond represents an electron cloud, negatively charged region. The negative repel, and therefore those bonds, electron densities, will try to stay away from each other as far as they can. That is the Vesper model. And based on that, the angles they created, the theoretical values, calculated values, and it matches perfectly fine in terms of experimental values, is 109.5 degrees, 109.5 degrees. And therefore that's a tetrahedral. Tetrahedral means tetra, 4 hydral electron regions. That's a Vesper model. We also talked about the AX3. It's a triangular planar, and the bond angle is 120. So it's a equilateral triangle, so the bond angle outside is 120 times 3, 360, right? The whole thing. We also talked about the linear molecules. As the linear molecules are AX2 types, is the central atom, 2x are on both sides, and the bond angle is always AX is 180 degrees. Then we talked about some of those molecules, that some of the molecules looks like it's a X3 or X2, but in fact they're tetrahedral. For example, ammonia that I gave you before, the example before, ammonia, in fact, it has a 4 electron region, and those electron region basically using the lone pair. 1 bond, 2 bond, 3 bonds, and the lone pair that considered as another electron cloud. This electron cloud is not, these 2 electrons never shared with any atoms, therefore it repels towards this bond, and the bond angle, and this bond angle squeezes a little bit, and that's basically squeezing is 2.2 degrees, and that's why it's 107.3 as opposed to 109.5. So why it is so? Because of the lone pair. Likewise, if you look at the water molecule, it is 2 pairs of lone pairs oxygen. So it's basically 4 electron clouds, and those electron clouds, you can just put it like this way, another Mickey Mouse like this side, and those 2 electrons right there. And since these 2 electrons are discrete electron clouds, it's not sharing with anybody, and therefore this bond angle is squeezes, and the bond angle is H bond angle. Basically, we're talking about this bond angle is squeezing a little bit. That is 104.5. That is, it squeezes by 5 degrees. And why it is so? Because it has the goes to other one. Because it has the 2 pairs of lone pairs on oxygen, and they repel very strongly. That's why this squeezes the bond angle. So these type of questions will be entertained, will be there in the test, one way or another. Either phrased in a way that you must understand why the bond angle is 104.5 as opposed to 109.5, which is perfect tetrahedral. Next, we'll go to the X3 types. So X3 types, one such example is a formaldehyde, and formaldehyde has the C, you already have it here, CH2O. The general structure, the molecular formula is CH2O. Once you make the Lewis dot structure, HCHC, and it's double bond O, and oxygen has two pairs of lone pairs as usual, and that's basically a double bond right here. And oxygen also has a lone pair, one this side, for example, and another is this side, for example. All right. So because of the lone pair, so now we're talking about this bond angle, right? HCH, or you can also see HCH and HCO and HCO. So we are talking about these bond angles, right? So this bond angle will be 120 according to our calculation. 120 degrees, right? It's a pyramidal structure, a triangular pyramidal. It will be 120 degrees, but in principle, so is this one, but it is 116.5, 116.5. So it is less than about 3.5 degree less. You can tell me why? Why the bond angle is 116.5, not 120 degrees? Who can tell me why? What could be the reason? Anyone? What could be the reason the bond angle is not 120 degrees? Perfect triangular planar. Anyone? Yes? Any idea?
Because of the lone pairs?
Yeah, so basically what is happening, this one is squeezing to this side and this one is squeezing to this side. That is correct. Just discrete electron density, and therefore this bond angle HC and H bond angle, HCH bond angle is not 120 because it's squeezed a little bit. Squeezing coming from the lone pairs of oxygen, two pairs of lone pairs on oxygen, and therefore it is 116.5. So this kind of questions we can ask, okay? All right, so triangular planar molecules, the bond angle is not 120 degrees because of two pairs of lone pair on oxygen. It's repelling the electron density right here, electron density right there. So it's squeezed a little bit, okay? Let's go to the next one. This is the acetylene and this is ethylene. Ethylene is, remember, ethylene is a C2H4, and you already did that. C2H4 is the molecular formula. And
I have a question.
Yeah.
How do you know that it's triangular planar versus tetrahedral? Because
So it's X3, AX3. So this is our the A, 1, 2, and 3. 1, 2, and 3. X3 type. Remember the X3 type is a triangular planar. X4 type is tetrahedral. X2 type is a linear. So it is
then why is H2O tetrahedral?
because the lone pairs. Because the lone pairs right here. It is a 4 electron cloud. 1, 2, 3, 4. 1, 2, 3, 4. So there are electron clouds there. Yeah.
Right.
Yep.
But then CH2O has lone pairs as well.
CH2, but we're not considering this lone pair. We're considering this bond, this, and this. So it's a triangular triangle. It's a triangle set. We're considering HCH, HCO, HCO. So if you consider this oxygen, but this oxygen has a double bond. Whenever you have a double bond, it's always planar because double bond cannot make any three-dimensional structure.
Okay.
Yep. Go to the X2 type. So this is also X3 type, another example of X3 type, by the way. So this is the X3 type. C2H4 is a ethylene, and once you draw the Lewis dot structure, HCH, double bond, and one is a pi bond. Everybody knows, right? One is a pi bond, the rest of them are sigma bond. It's a pi bond. Pi bond means it's a pi electron. I remember pi bonds are pi electrons. Pi electrons are mobile, flexible. So they can go to this direction, they can go to this direction. When they're going to this direction, squeezing the bond angle a little bit. When they're going to this direction, squeezing the bond angle a little bit. They're mobile, they fluctuate. And therefore, it is not 120 degrees as it should be. It is 117.2. a little bit less. Now this squeezing, this less is not due to the lone pair. It's due to the pi bonds, pi electrons. Pi electrons, once again, pi electrons are mobile. Pi electrons are mobile pi electrons. Mobile pi electrons are always mobile, meaning they can go this direction, they can go the other direction, and as they do, sigma bond cannot. Sigma bonds are fixed. So since pi bond can move to left side, squeezing the bond HCH, it can go to the right side when squeezing this HCH, and therefore squeezing the bond to 117.2. So now this squeezing is not due to the lone pair, due to the mobility of the pi electrons, the pi bond. The question could be asked, right? Remember, these are not the same principle doesn't apply to some other molecules. For example, right here. Let's go to the X2 types. Acetylene, remember acetylene, you have a C2H2, acetylene, and you already know, I already asked the question, it is a 2 pi bonds. You have a 1 and 2, and 1, 2, and 3, they are sigma bonds. But in this case, whatever you do, the bond angle will never change. It will always 180 degrees. It is a straight line, right? You can say, why not? So let's assume you have a pi bond, pi electron right there, you have a pi electron right there, you have a pi electrons right here, and pi electrons right here. Fine. So now when these two pi electrons are going to these directions, this is moving to these directions, right? And these two pi electrons are moving to this direction, right? Similarly, if they're moving to these directions, these two pi electrons will move into this direction. So whatever they do, you make a straight line anyway like this. It's a straight line, right? It's a straight line. So
How
since
do you know those are there?
how do you know which is there?
How do you know that those are there?
So remember when you draw the Lewis dot structure, C2H2, we have H, C, and H. Remember, that's our Lewis dot structure. Now, this carbon has 1 electron. So what is this? Carbon has 4 electrons outside cell. This has 2. This has 2. And these are the 2. So this electrons is this one. This electrons is this one. This electron is this one. And this electron is this one. So remember, they made a bond, a pi bond, but pi bonds are mobile, meaning they can fluctuate. They can go back and forth, back and forth, back and forth. That's why these molecules are reactive. They make compounds, many compounds. Thousands of compounds in fact. All right, so that's they are already there because of the carbon has 2 electrons. These 2 electrons are not shared. They make a pi bond. Pi bonds are mobile bonds. Now these 2 pi bonds, since electron density, if it moves to this side, this will move to this side. As it moves to this side, this electron density will go to this side. This will go to move this side. This will move this side, and this will move this side. Basically, this molecule is rotating. It's a rotational motion. It creates a rotational motion. Irrespective of motion, whatever it is, the rotational motion remains in a straight line always. And straight line means 180 degrees, and that's why this bond angle is 180 degrees. It never changes. As you can see, perfect 180 degrees and perfect 180 degrees. Another molecule, that's acetylene. Another molecule is carbon dioxide. If you draw the structure of carbon dioxide, the Lewis dot structure, it looks like this, right? It happened exactly the same thing. You have a this is a double bond, right? So you have a pi electrons right there, another pi bond, the lone pair right there, and the lone pair right there, lone pair right there. Once again, if this lone pair move to this side, this will move to this side, then this will move to this side, and this will move to this side. This is rotating, molecule is rotating. So the bond angle is oxygen, carbon, oxygen is never changing. It's 180 degrees. So linear molecules, irrespective of they have a double bond, I don't think there's a triple bond, a double bond, triple bond, lone pairs of oxygen or pi bonds in a carbons, irrespective of whatever it is, they always in a straight line. There's no deflection from this 180 degrees, and the only thing, this creates the molecular motion. Although this is a straight line, it never been fixed, never stays as a straight line all the time. It's rotating, all the time it's rotating, and that gives the rotational motion of the molecular compounds. As you know, all molecules are rotating, vibrating, doing lots of under the sun. That's what they do. So remember this. This is the molecule that you see right here. Is a combination, linear molecules are the combination of pi bonds as well as the lone pairs on oxygen. They can also do the fluctuation like this. All right. Any questions so far? Because we are done in terms of the molecular shape, the molecular compound, the 3D structure of the molecular compounds. Any questions? Please ask. Because these.
I just have a question. So in C2H2, you were talking about how the carbons had 4 in the valence shell, and then they like bonded together, which makes a triple bond. But then on the 3D model, you drew the electrons like they were in their own cloud.
Mm-hmm.
Like, did you draw that to just show us? But in reality, those electrons are bonded with the triple bonds?
That is correct. That's the reality. Means this triple bond, although this is a bond, but it is not. It is a very mobile, very flexible. You can make and break, and that's why these molecules are very, very reactive. This make a compound, many compounds. We'll talk about down the road later on. That is correct. As I just showed how they're made and what they mean by that. Yes. And that also creates the very important part, as I told you, that creates the molecular motion. Motion means molecule is moving, rotating, vibrating, doing all sorts of things doing under the sun. We cannot see it, but if you put them in electron microscope, high resolution electron microscope, you can see them. Those pi bonds are fluctuating. Sometimes this side, and molecule is rotating. That is right. Any other questions? Any other questions? So this is the molecular structure of the molecular compound. I gave you many of those, and I'll give you a few more. Now, what I'm going to do is as follows. I'm going to, let me see how much time I have. I have plenty of time, and I'm going to take you to the white blackboard, and I'm going to ask some questions, and you have to do it because we already talked about those things. And I'm going to end the source for this. Then I'm going to take you to the white blackboard, and I'll tell you why. Because it's very important to understand this concept, the molecular structure that we already did. And let's go to the white blackboard, and everybody can see it. Now, I'm going to ask you, draw the structure of, all right? Draw, please write down, this kind of test will be there. Draw the structure, 3D structure, of course. 3D structure of, please don't write, I'm doing it. So please do structure of, oh my goodness, this is my cursor, huh? So structure, 3D structure of this molecule, CH3. Please write down, it will be the test, a similar kind of question will be the test. CHO. Does anyone know what's the name of this? I already gave this molecule before. Does anyone know what's the name of this? Anyone? Does anyone know what's the name of this? Yes? Yes? Acetaldehyde. Draw the Lewis dot structure, draw the three-dimensional structure of this molecule. Can you do it for me? You have 2 carbons. Carbon number 1, carbon number 2. I'm going to write carbon number 1 and carbon number 2. Can someone help me here? Tell me, what do you want to do? Yes? I am waiting.
I think you start with the 2 carbons in the middle with a single bond between them. And then for the carbon on the left, there's 3 hydrogens, all single bonds. And then the carbon on the right, there's a double bond with the oxygen and then a single bond with another hydrogen.
Yeah, what you just told me is a Lewis dot structure. Very good, but I want the 3D structures. Yeah, you said it right. It's a Lewis dot structure that you gave me. I want the 3D structures. So let me write down. So carbon number 1. Tell me carbon number 1. Let me draw it here since you told me that's perfectly fine. Let's draw it here first. The Lewis dot structure, then we'll go to 3D structure. Okay? Very good. You said it fine. I'm going to do it for you. So that's basically you said, I remember. C. C. Double bond O and H. That's what you told me, right? Yes or no? Yeah? Now that's basically, I think you said this is Lewis dot structure, LDS. I want a 3D structure. Can you do the 3D structure for carbon number 1 and carbon number 2? Is carbon number 1 X4, X3, or X2 type? Carbon number 1, C1. This is the X4 type, X3 type, or X2 type? Anyone? Come on, please. Come on. Carbon number 1.
X4.
Very good. That means it's a tetrahedral, yes or no? It's a tetrahedral, yes or no? Yeah?
I guess.
That is right. So let's do the tetrahedral. This. So that's our C1 and C2 bond. And one goes like this. One H like there. And like there. Tell me yes or no. That's a tetrahedral. The carbon number 1. Yes? And what's the bond angle here? Come on. What's the bond angle here? 109.5 degrees. So carbon number 1 is a tetrahedral. 109.5 degrees. Our carbon number 2. You can do the carbon number 2 for me.
Would that also be 109.5, like the bond angle, or are you asking for the shape of the carbon too?
The shape of the carbon is a tetrahedral. One angle of the HCH is 109.5 degrees because a tetrahedral. Tetrahedrals are always 1.9.5 degrees. So carbon number 1 is a tetrahedral, 109.5 degrees bond angle HCH. How about carbon number 2? What is this type? Carbon number 2 is X4 type, X3 types, or X2 type?
Is it 3?
Excellent. That is correct. AX3 type. AX3 type. This carbon number 1 is AX4 type. That's a tetrahedral. Why? 1, 2, and 3. That's the one. That is absolutely right. Absolutely right. So that means, what's the bond angle here? So this is the X3 types. What's the structure of, what is the 3D structure of C2? What is the 3D structure of C2?
Is it trigonal planar?
Triangular planar. Bond angle? What's the bond angle?
Is it
120.
120?
It should be 120, but in principle it will be 117.6. Yes or no? Because of the lone pair of oxygen. Yes? All right. Because of the lone pair of oxygen. We did it. Remember, we did it just a few minutes ago. That's what we did it. CH2O. That's a 1H instead of H. It's a carbon. Another hydrogen. Instead of hydrogen, it's a carbon. Carbon 1. And that's a. If you have a hydrogen, it's a formaldehyde. But it's a carbon is linked like there. So similar kind of bond. One is H and double bond. So basically, this bond angle is 117.3 or 70.5, something like that, right? 70.3 that I gave you before. Yeah. So that's basically this is the X4 type, this X3
What
type.
happened?
X4 type, X3 type. Now I want you to. So this is one such question will be asked in the test. Definitely will be asked in the test. I'm going to give you another example, the same type, and you do it at home. And I'll discuss on Friday if necessary, and you will tell me. So draw the 3D structure of number 1 is this acetaldehyde, number 2 is vinegar, acetic acid. Please write down and you do it at home. CH3, C, O, O, and H. That's acetic acid. So that's acetaldehyde, it's acetic acid. You must do it because one of the two or maybe both will be in the test. So you are supposed to do the structure of C1 and 3D structure and the bond angle and carbon number 2. So C1 and C2 and X4 types, X3 types, X2 types, You apply and do it. Is it okay? Yes or no? You do it. I'm going to take you to the again. I'm going to close this one. Everybody has it, right? Yes or no? All right. Since you have it, I'm going to close this. Now I'm going to go to that. Now the same thing. I'm going to share the screen again. You guys still have 8 minutes, okay? All right. Share the screen, and that is our right here. Right here. All right. So this is the one. This is a summary, and we applied those two into 2 different molecules. Those will be very important to ask. So please remember, okay? All right. And you can do it now. Next one. Next characteristics of the molecules, of the molecular compounds. And one of the most important properties or characteristics of the molecular compound is the polarity. Polarity means dipole, negative pole, positive pole, or the north south pole. That's where the name came from. The polarity of the molecule, delta positive, delta negative, or positive, negative. That's the polarity. So one of the most important properties of the molecular compound is the polarity. What is the polarity? So although all covalent bonds involve sharing of electron pair, but they differ in degree of sharing. Why do they differ in degree of sharing? Because all the elements in the periodic table that you saw, they have another property is called electronegativity. Electronegativity. Metals have electropositivity. They lose electrons to become positive charge. Non-metals and metalloids, they share electrons. They accept electrons to make a covalent bonds. So when they accept covalent bond, that is called electronegativity. Negative, because after taking the electron, they become a negative charge. So they call electronegativity. Or it also has another name called electron affinity. AFINITY. Electron affinity. Affinity means the attraction towards electron. Sorry. When they make a covalent bond, 2 electrons, one covalent bond means 2 electrons. Are they shared equally? Answer is no. That degree of sharing depends upon the electronegativity or electron affinity of the atom. And so, and that's basically that's it. And when you have a bond, for example, let's say if you have a molecule like A, covalent bond, B, it's a covalent bond, just simple one. This is a 2 electrons. This sharing of the 2 electrons depend upon the electronegativity of A and electronegativity of the B. If they have the same electronegativity, for example, hydrogen, H, hydrogen, or any kind of diatomic elements, electronegativity of this hydrogen and electronegativity of this hydrogen are the same. But they are sharing equally, 50-50, no problem. When you have 2 different elements, atoms, they share differently. So electronegativity, and how do you calculate the electronegativity? You take the electronegativity En of A, and minus En, electronegativity En of B, and you take the absolute value. So electronegativity of A minus electronegativity of B, that will tell you whether this bond is polar or non-polar. If the electronegativity of diatomic elements, the chlorine, bromine, iodine, hydrogen, nitrogen, oxygen, they're the same. Electronegativity of H, electronegativity of A, and electronegativity of B are the same. Therefore, no polarity. If A and B are different, then there will be some residuals, there will be some number. If that number is less than 0.5, if that number is less than 0.5, it's a non-polar covalent bond. The bond type is non-polar covalent bond. Non-polar, meaning there is no polarity, no positive direct charge. And usually the most likely to be formed between 2 nonmetals, same nonmetals, or a nonmetal and a metalloid. Non-metal and metalloid. And I'll give you some plenty of examples. if that difference, electronegativity of A minus electronegativity of B, that difference is 0.5 to 1.9. You must remember this table. 0.5 to 1.9 is a polar covalent bond. Polar covalent bond. Two nonmetals or nonmetals and metalloids, they also make similar kind of things. So nonmetals and metalloids, they can make a non-polar covalent bond. They can also make a polar covalent bond. And we'll take plenty of example for this, okay? If the electronegativity difference of A and B are greater than 1.9, then it's ionic bond. Remember which ionic bond we talked about, right? The donating electrons, metals lose electrons, non-metal gain electrons. Usually, if you look at the electronegativity of those metals and non-metals, they're always greater than 1.9. So once again, if you have a covalent bond between A and B, if the electronegativity difference between the two atoms is 0, it's a non-polar. If the electronegativity difference is less than 0.5, 0 to 0.5, then it is less than 0.5. If it's greater than 0.5, with polar. So less than 0.5, 0 to 0.5, it is a non-polar covalent bond. If it is 0.5 to 109, polar covalent bond, and greater than 1.9 is the ionic bond. So remember, you must remember this table in order to determine whether the molecule is a polar or non-polar. This is, you do not have to remember this, but I'm going to show you. Electronegativity is the electron affinity. This is called Pauling's scale. Pauling is the name of the scientist who discovered the electronic configuration of the atoms, electronic structure of the atoms. He got the Nobel Prize twice. One for the atomic structure, and one for the Peace Prize. One cannot get the same prize for the same thing. Pauling's scale, according to the Pauling's scale, electronegativity scale, fluorine is taken as a standard. It's a 4.0 maximum. It's arbitrary number, maximum 4.0. So electronegativity of fluorine is 4.0. According to the Pauling scale, Pauling, P-A-U-L-I-N-G, Pauling is the name of the scientist, okay, last name. So Pauling scale, fluorine is taken as a standard, 4.0. Based on fluorine, rest of them are basically standardized, calculated value. Oxygen, 3.5. Nitrogen, 3.0. Don't have to remember. If I ask you a question, and I'll give you these values. Carbon, 2.5. Boron, 2.0. If you go to the beryllium and lithium, they also have some 1.0, 1.5, and something like that. Remember, the metals make a ionic compound, so we are not into that directions, but we'll be within this vicinity, the non-metals and metalloids. Fluorine, after the fluorine, it's a second period, 3.0. All right, I think my time is up, and it's going down and down and down. Oxygen is going 2.5, 2.4, and going down. So as this, and as you can see from the example. So Friday, I'll put this slide again in the blackboard. So try to remember some, but you don't have to remember. We'll work out, and we'll give some plenty of example of molecules and see which one is a polar, which is a non-polar, and we'll give some generalization from there. Hydrogen is 2.1. Remember, hydrogen is 2.1, carbon is 2.5. Very important. All right. So I have only, now can someone tell me this molecule is a CH4. Is it a polar or non-polar? I'm going to leave it to you to answer the question. CH4 is a methane. CH4, is it a polar or non-polar? Is it a polar or non-polar?
Mr. Bottom, it's 11:50.
I'm done. This is my last question.
Is it a polar?
Or non-polar?
It's non-polar. Oh.
Then someone said polar, someone said non-polar. I don't know which one I take. So it explained. Can you explain to me why? We'll do it Friday. Everybody. Is it okay? Yeah. All right. I'm going to leave it to you like this, and I'm going to close things right here. All right. Okay.
Professor Dada,
Yes.
this is Sabrina Vaughn. I'm just making sure you know I'm here.
Hi, Sabrina. Good to hear from you.
Yeah, I'm here.
I know. Yeah. Looks like we're in touch all the time, huh? Yes.
Yeah.
I know you're here. You're fine. Okay.
Thank you.
You're welcome.
Dr.